My name's Tadhg, and before anyone asks, yes, that is how you spell my name correctly. Today I'm going to be talking about machine learning applications to planetary magnetospheric signatures. So one of the first things I always like to show is just a simple planetary magnetosphere in action. This is probably a very familiar kind of picture to most people. So we have here is a planet with its own magnetosphere immersed in some solar wind. And then I just had, there's a big strong burst of solar wind comes in from the left-hand side of the screen, and it causes a compression on the magnetic structure of the planet. Again, don't want to keep jumping ahead of me like that. Notably in the tail, you can kind of see there's like some kind of coiled structure in there, and then once the pressure changes, you end up getting that feature. It ends up being like ejected and shot down tail, and you get this nice kind of well-defined X line in the center of the screen there, where the magnetic field kind of pinches together really, really close. And that is a really optimal location for magnetospheric reconnection, like ongoing as well. So I have here just a nice little simple model of reconnection, how it occurs, where it occurs, and what we see. So reconnection occurs at this, as I've indicated here, reconnection site, also known as like an X site. This is where the magnetic field lines physically will touch together, reconnect, and then separate. And a spacecraft would ideally be able to, if it was located at this location, be able to identify the reconnection occurring through, measurements of the plasma and the ions. But unfortunately, since we're usually dealing with a single spacecraft orbiting a planet, it doesn't really get into those locations very often. So instead, what we can do is we can actually identify signatures of these reconnection events in the magnetic field data of the spacecraft as they're observing. So instead, if you have a spacecraft that's down tail, when reconnection occurs, it'll create these little plasma bubbles called plasmoids, which will shoot down the current sheet. And if one of these plasma bubbles passes over your spacecraft, you'll end up seeing a nice characteristic deflection in the magnetic field lines. So as you can see on the bottom here, you have some it'll peak up, it'll drop down, like inverse polarity, and then come back to the background. And depending upon how close you are to these events will depend upon the strength of the structure. And if you're not sometimes even if you're not in the event, but you're in like the nearby, magnetic field structure in the current sheet, the bulge caused by those plasma bubbles will, create a compression that you can identify. Meanwhile, on the day side, you can get dipolarizations, which are a similar enough feature, and they create a very similar signature in your magnetic field data, just with a inverse structure where it goes inverse first and then it'll peak up afterwards and then return back to normal. But this is, of course, a very ideal case scenario. So what we're looking to do is identify these features, these signatures of reconnection in a spacecraft that's just orbiting a planet. So we're choosing, for this instance, the Cassini spacecraft orbiting around Saturn. And we're applying a supervised learning method. We're going to be applying this to the Smith et al. Catalog from 2016, which was a semi-automated method to identify these structures, these signatures. And on the left-hand side, you can actually see what they identified. What they identified and what the actual signatures were at that time. So most notably in the B theta measurement, you can see that kind of characteristic deflection. I should have updated the slides, but you can see that characteristic deflection, but it's just not quite as perfect as that model we showed before earlier. And at the very top, you can see the actual duration it's occurring across, where purple is there's no event happening and the yellow is that there's an event occurring. And they are, as you can see there, we're trying to kind of classify these we're trying to classify these temporal features with hard to find boundaries. But they don't, in reality, they don't actually have these hard to find boundaries. It doesn't really recover in that time span, which obviously introduces issues and problems. So the Smith catalog that I mentioned has around 2,000 detections across 2006, 2009, 2010 of magnetotail detections. Fantastic. We can apply some machine learning to this and then hopefully extrapolate what they identified and what their semi-automated method, which was then human verified. We can kind of try and apply, make a machine learning algorithm that will help to see what the machine and the person working in tandem identified. So one of the simplest ways we could think of to do this, I won't go through all the ways we tried that didn't work, but the simplest method we thought of was we would take a single slice in time when an event was occurring or not occurring, And since these features are temporal in nature, we took the preceding 15 minutes and the following 15 minutes to try and actually identify that structure. And we fed all of the magnetic components in. Oh, it's rushing ahead of me. I don't know why it's doing that. We took all those components and we fed those into a simple feed-forward neural network. So our training inputs would be just a suturing together of these magnetic field structures, and then our training output would be a binary 1 for an event occurring, or a binary 0 if an event is not occurring. And then what we can do is we can create basically a minute-wise catalog of these events. So essentially, artificially inflating we're inflating our 2,000 events to actually cover an individual identification for every minute of an event occurring. So our next observation will be if we just shifted these this identification period, like and our window of observation over slightly, and that's also considered a 1 for our training output. And similarly, we can just do the exact same thing for our training zeros. We can take a single moment outside of the outside when an event isn't occurring, and take the 30-minute window around that and say, okay, there we go. There's our magnetic field when an event isn't occurring. So we built the model, and it seems to work quite well. It's created this here is a comparison of our model, the machine learning model, to the Smith model from 2016. Blue, so the black background is just what the B-theta component of the magnetic field was doing at that time. The blue identifications are where the Smith catalog said something was going on. The red are where ours are saying something's going on. And immediately you can see that there's actually a significantly larger number of red identifications than blue identifications, which would indicate a failure of the machine learning model. I'll tell you now why this isn't a failure, because this is one of the strengths that machine learning kind of has that a human observer or even a hand-built model doesn't. Is a human-built model will have inbuilt thresholds that they have to meet for them to say, okay, now this is an event. So for example, the Smith catalog had minimal B-theta deflections that they had to meet. There had to be a signal to noise background level that had to meet. There had to be durations and everything, loads of and also I think there was a fitting parameter threshold that it needed to meet. But these are hard-coded thresholds, where in reality your events are a lot more variable in nature than that, and you can have smaller events than this threshold. They're just hard to identify. So instead of looking at it in this global scale, if we actually compare how our model did and the Smith model did, if we apply the exact same threshold across the board, basically comparing like with like, and we ended up with this nice and simple little confusion matrix, where we had pretty good identification of observed nulls and observed events, and then there was a significant but not uncontrollable number of failures. So our false positives and false negatives weren't too extreme. All this work. So this is the work that was published actually, or is under publication, but accepted for publication and approved, and we're just waiting for them to actually publish it in Frontiers. I have it as Garton et al. 2020, but that unfortunately, by the way, maybe the COVID delays made it being 2021. So the way we created our model, as I mentioned, this was from the Smith catalog, occurred across observation from 2006, the latter half of 2009, and 2010. So that actually creates a very small window of observations for our model to go off of, and also only focused on magnetotail events. But we wanted the model to work across everything. So we would just feed it in all of the Cassini observations for its entire near Saturn lifetime, and it would just spit back out our identifications. And this worked really reasonably well. But because the Smith catalog was focused in these areas, we couldn't validate these features that either occurred on the day side or occurred outside of these temporal windows, because the background environment was different. There's actually a fantastic paper, I think, from based on ecological photography and applications of machine learning to that, where if you actually change the background environment, it can drastically change how effective your model is at identifying classes within. So this kind of, I believe, feeds into the general idea that I'm sure every single one of us has come to at some point when trying to talk about machine learning to the wider planetary science community, which is people will tend to say, it's a black box, you can't trust it, or you can't, you can't know for sure. And we already know that, hey, it's performed, its job, it's done its validation, and it works. And it's kind of because of this that's where that mentality is, I think, the both of them crash, because it's entering into new environments that we can't really control. It's not the perfect lab environment that would be ideal for a machine learning algorithm to apply to. So there are methods that we try to kind of get around this problem. Is we're trying to meet planetary science, like the old school planetary scientists, somewhat more in the middle, where we can show, look, if we show the model is consistent, at the very least that adds a bit more weight to what we're saying in these extra areas where the model is outside of the perfect radius and the perfect local time window. So the best method we thought was if we would run the model a number of times with different train test splits, the same proportion of train test splits, but just taking different events from this event was in the training in run one, so now it's going to be in the test in run one, and we'll fill in its place with a different one. And that was just done randomly across 5 different times. And what we observed was, not unsurprisingly, when you change which elements you're training on, it changes somewhat what elements you're able to identify. The accuracy across the board and the confusion matrix was identical, but it was just identifying different events. So instead, what you can see here is a comparison of the 5 runs and how they identified delta b, the events in terms of delta b theta. So our distribution of how much did the algorithms, how much did the same model agree with itself when run on different training sets for, we'll say, a 5 nanotesla deflection. Does it say that it identifies 100 events and it's the same 100 events as the previous model, or does it identify 100 events but there's only 20 that are the same? So we came up with this probability of variance metric, which is essentially if both of them agree on half of them, it's 0.5 variance. If they agree on 90% of them, then there's there's only 0.1 variance, and so on. And what you can see is for these very small deflections, the harder to identify ones, you get more of this increase in variance. And that may just be due to not training on them. You may not have seen as many small scale deflections in your training. So this is only for the delta b theta events, but you can apply this to a number of metrics. So the signal to noise ratio, how long the events are. I think there are a few others that we took down, but I can't remember off the top of my head. And we combined all of them together into these 3 different comparisons here, where you have the exact same comparison of how much the runs agree with one another, which is averaged across the board. So, for example, the delta b theta here, you can see that for the most part, once you get above this threshold of 0.71, they agree. All the models agree relatively consistently with one another. They 90% agree with each other. Whereas below that, that's where your variance, kind of shoots up a bit more. And the same happens for our delta t. Our delta, our duration, and our signal to noise ratio. So then when we're actually applying and doing more physical, we can exclude these variable results, and we can exclude these variable results and only look at ones we can say with a reasonable level of confidence. And I think personally that will end up standing more to essentially spreading the word of machine learning to the older generations and kind of encouraging them to accept it with more open arms for the strong tool that we know it to be. So I know that was a very quick jump around, but I can kind of recover everything I said. So essentially, temporal features in magnetic field data, they can be identified in 1D or 1.5D data sets through our machine learning models. I'm sure that's no surprise to anyone who's here. But space scientists face unique trials in extrapolating machine learning models to unique environments. Anyone else can, easily go out and take 100 pictures of swans, and then we need to have a couple of them where they're in ponds, and do that quite easily. For us, it's not quite as easy as that. So maybe the best method to the best method to solve that problem is to try and reach for these more confidence and apply these a bit more validation to our models through this method of changing up the training set and seeing how it performs on these extrapolated data sets. That's going to be everything from me. I hope everyone enjoyed the talk, and I'm open for questions.